Video, we're going to look at a couple of problems which caused my A-level students quite a few problems in a recent test. They're both past paper questions, and they're really going to be the sort of questions going to be the difference between getting A grades and A-star grades and not getting those grades. The key things to remember, especially in the first one, is clear diagrams and setting out your model properly. So without further ado, let's get into the first question. So here it is. We've got a block B is placed on a plane inclined at 30 degrees. Particle P here, mass 0.6 kilograms, is placed on the upper surface of B. Particle P is attached to one end of a light inextensible string that passes over a smooth pulley. That means there's no friction. Fixed to the top of the plane. A particle Q, mass 0.5, is attached to the other end of the string. The portion of the string attached to P is parallel to the line of graded slope. So this means that this is moving parallel to here. So the force will be parallel to the plane. Any force is in the string. The string is taut and Q is vertical here. The particles release from rest and start to move at acceleration 1.4 meters per second squared. It is given that B is in equilibrium while P moves in its upper surface. So B is in equilibrium, so it doesn't move, and P moves along it. So what we're going to do, we're going to start this question by looking at P and Q, because it says find the tension in the string while P and B are in contact. So find the tension in the string while P and B are in contact. Well, actually, the simplest way, ironically, is not to look at necessarily P, it's probably to look more at Q. But anyway, let's draw all our forces on the system. So if we've got Q here, we're going to have its weight going down. And Q was 0.5 kilograms, so it's 0.5 G. G being, we're going to use G as equal to 9.8 meters per second in this question. And then we've got the tension going up. Now the tension is consistent from in the system. So as far as P is concerned, the tension will be going that way. The string will be pulling it up the plane. Whereas Q feels the tension going that way. Now P is also going to have friction on the surface of the block, so it's going to have friction. I'm going to use FR for friction, and we're going to have a normal reaction on the block, so we'll call that R, and we're also going to have its weight acting on the block. Notice I've just drawn a line for the top of B to indicate the surface. Okay, so I've drawn the line on top of B to indicate the surface. We don't need to examine what goes on with B because we're looking at PQ system here, and we've got the weight of P was 0.6 G, and we got our angle here is going to be 30 degrees, and our angle here is also going to be 30 degrees, because if you go along here you get a right angle because it's vertical and that's horizontal, so that's 90 minus 30, and this therefore is going to be 30 if you take that away from 90. So that will allow you to get that 30. So along this side we're going to be dealing with causes, and along this side we're going to be dealing with sines. Now if you don't know how to resolve this force in these two directions, then you really need to look at a video on how to just do basic resolving. Okay. Now what we can see is we've got the acceleration going this way, 1.4 meters per second squared, and we know the mass and therefore the weight. And we know the resultant force from this, because that's just equal to mass times acceleration. Notice I said resultant force equals mass times acceleration. A lot of people think it's just any force that equals to mass times acceleration. It's the resultant of this one, take away the tension. So we've got actually an equation here with only one known, the tension. So let's just solve on Q. So if we resolve on Q, and we're going to do that vertically, or we're going to at least assume downwards is our positive direction. Then we've got MA, which is going to be 0.5 times 1.4 equals 0.5 G minus the tension. So therefore the tension is going to be equal to 0.5 times 9.8 minus 0.5 times 1.4. And when we work that all out, we get 4.2 newtons. Now what you'll see is I've drawn a little table here to make things a little bit easier when it comes to doing this system. And if you're not certain, you can use a table to do these ones if you're a bit uncertain here, but we're going, because this one's a bit more complicated, I'm going to do a table of all the forces acting on P, because if I'm going to find the coefficient of friction between P and B, so P is that ball, there's the surface of B, so that's going to be dealing with FR, then I'm going to need to resolve this more complicated system here. So let's look at this. So we're on P here, and there's two obvious directions, parallel to the plane and perpendicular to the plane to resolve in. So we're going to look at perpendicular to the plane, and we're also going to look at parallel to the plane. And those are going to be my two positive directions where the arrowheads go. So I've got the forces acting on P are T, 0.6 G, FR, friction, and the normal reaction. And there's no other force acting. I always write down the resultant force down here, because all these things must add up to the resultant force. Now, perpendicular, how much of T acts perpendicular to the plane? Well, as it's at right angles, none of it will act perpendicular to the plane. 0. 0.6 G. Well, if we take this side here, that's going to be 0.6 G cos 30. Okay, so, but it's in the opposite direction. That's up, this is going to be down, so it's going to be minus 0.6 G cos of 30. FR, none of it's going to act. Normal reaction is acting in the positive direction, so that's that. And there's no resultant. The acceleration is in this direction for this string. It's going to be in that direction for this string. The resultant, therefore, is in that direction as well. So there's going to be no resultant force acting perpendicular, so it's 0. Now, we're going parallel. All of T acts up the plane. We've got minus 0.6, and this side here is going to be 0.6 G sine 30. Now, if you don't know where that comes from, we're basically examining this triangle here, where this is a right angle, and this side is the equivalent hypotenuse, and its length is 0.6 G. So therefore, as that's the opposite, it'll be 0.6 G sine theta. And that's going to be negative because it's acting that way, whereas positive is that way. So 0.6 G sine of 30. How much of friction is acting down the plane? All of it acts down the plane. Note the negative sign because it's down the plane. All right, this is just this is accelerating this way, so therefore the friction must oppose this motion. The reaction is going to be 0, and the resultant force is going to be ma. Now we know m is 0.6, and we know a is 1.4 meters per second squared, so that's going to be 0.6 times 1.4. Now we can write out both of these systems as an equation now. So if we just look at perpendicular on P, so that's this column here, we got, I'm going to put the R first because it's positive, R minus 0.6 G cos 30 will equal the resultant. Everything else is 0. 0. So therefore R equals 0.6 G cos of 30. And if we wanted to work that out, cos of 30 is equal to root 3 over 2. So effectively, that's 6/10 times by root 3 over 2. So 6 root 3 G over 20 is what you come out with that. You can work out the calculator value if you want. Now let's go parallel on P. So we have T minus 0.6 G sine 30 minus FR plus 0 equals MA. 0.6 times 1.4. Now let's give us a little bit more space to work with down here. Oops, there's some working I did before when I was checking through this that I rubbed out. Right, so we got T minus 0.6 G sine 30 minus FR equals this. Well, we know that FR equals mu times this, and we don't know what mu is because that's what we're looking for, the coefficient of friction. Okay, remember FR, friction, equals mu R. So I'm going to replace this with mu times all of this. Now, our tension is 4.2, so let's put that in. And 0.6 G sine 30 comes out to be 2.94 minus mu times by all of this, 6 root 3 g over 20, and that's going to be equal to 0.84. So we can work this all out, and we can put that into our calculator, and we can find out that mu equals 0.082 to two significant figures, or 3 decimal places, depending on what you're working to. So that gives us our value for mu. Given the weight of B is 7 newtons, calculate the possible values for the coefficient of friction between B and the plane. So here's B. I think this was P, wasn't it? And this was Q. But we're just going to be looking here anyway. Now, this is a little bit more complicated because we've got B sitting on a plane, okay? And there is a rough surface between B. It's not glued to the plane, so it could move up and down the plane given enough force. We've got P, and there's some friction between P and B. So P is going this way because of the tension, okay? And that is pulling this one up the plane. But that tension is not affecting B. What happens to B? Well, what happens to B is, let's put in some values of what's happening to B. The easiest one to put in is the weight, 7 newtons. Let's shove that one in. There we go. And then we've got the frictional force caused by P pulling up the plane. So let's just call that F1 because there's going to be 2 lots of frictions. We've got the normal reaction of B on the plane, or the plane on B. So this is the normal reaction of the plane pushing up on B. Now, this particle P has weight acting downwards, but it only acts through the normal of B, only acts that way on B. So the amount of weight of P is going to be this one. It's only going to be this component from P before, which was, if we go back up to our diagram before, we can see this component here was 0.6 g cos 30. That was the weight of P acting in that direction. Because it's only the contact amount that goes. The bit that goes this way, okay, it does not affect B. Okay, it's only the frictional force that's pulling up that affects B. Okay, so we get what's that going to be? 0.6 g cos 30 going that way. Okay, now we want to calculate the possible values of the coefficient of friction between B and the plane. Well, the maximum it can be is 1. Okay, mu equals 1 is the maximum value of the friction. We want to try and work out what the lowest value of the friction will be. Now that's going to be, you could have either the friction going down that way, opposing the B trying to move up the plane, but because as F1 is only 0.42, that's when we calculate it, it's not, we can calculate from our previous question what F1 will be, because it's just going to be mu 0.82 times R, this value here. And that comes out to be, when you do that times by that, it comes out to be 0.42, which is going to be a lot less than 7 newtons component. So therefore, it's going to be the frictional force on B, between B and the plane here, is going to be F2 in this direction. Okay? Now, on B, that's all the forces we have. There are no other forces acting on B. We just got its weight, the friction between P and B, and the friction between B and the plane, and the normal reaction between the plane and B, and the reaction of P's weight on B going that way. Okay, so if we go perpendicular and we go parallel, we've got F1, we've got F2, we've got the 0.6 g cos 30, we've got the 7 newtons, and we've got R. And we've got our resultant. Although in this case, B is not moving, okay? So the resultant force on it is going to be 0. Now F1, we've got none of that acting perpendicular, we've got none of F2 acting perpendicular, we've got all of this acting downwards. It's minus 0.6 g cos 30. And then we've got, remember this is still going to be 30 degrees, so that's still going to be 30 degrees. So we've then got 7 cos 30 Now, a common mistake when my students are doing this is to put a G in here, but 7 newtons is the weight, so there's no need for G, because weight is a force, therefore it's taken into account the acceleration. And we've got R. And I just need to make this a minus, because this acts this way and positive is that way. On the parallel sections, we have got all of F1. We've got all of F2, and then we've got none of this, because this acts perpendicular, and then we've got a bit of 7 going that way, which is going to be the sine 30 bit. So we're going to, if that's positive, this could be minus 7 cos 30, and we can have none of R. So let's resolve perpendicular on B. So what we can see is I'm going to put R first because it's positive. And actually, I'm going to move everything to the other side of the equation just to save time. So this is going to go to the other side and going to be plus 0.6 g cos 30. Move this to the other side and I'm going to get plus 7 cos of 30. Now we know that F2 equals mu R. So that's going to equal to mu times all of this. Actually, I'm going to take the cos 30 out. So there's a common factor of cos 30 there. That's a very poorly written cos 30. Let's just write that out better. Cos 30. So we've got 0.6 g here and a plus 7 there. Now we're going to resolve parallel on B. And we get F1 plus F2 minus 7 cos 30 equals 0. Now we know that F2 equals all of this. And we know that F1, if we go back to our previous question, we can find out what F1 is. Because the friction here is just going to be equal to mu times that value there. So do 0.082 times 6 root 3g over 20. And that will give you 0.42 when you calculate it. So we've got 0.42 for the friction one here. So 0.42 plus mu times cos 30 times 0.6 g plus 7 minus 7 cos 30. If you want, you can work with decimals. No problem with working with decimals. You must keep all of the places in the memory so as you can do the calculation to the full accuracy at the end and then round at the very end. You must not round early, because if you round early, you can get some rounding errors and you don't get the right answer at the end. So we rearrange all of this and we get mu is equal to that, 7 cos 30, minus that, 0.42, divide by all of this. So divide by the cos 30, 0.6 g plus 7. Shove that into your calculators and you get 0.276 and so on out. So therefore, mu must be greater than or equal to 0.27623 S F. Moving on to our next question. Okay, what we have here is we have two forces of magnitude 6 newtons and 10 newtons separated by an angle of 110 degrees act on a particle P which rests on a horizontal surface. See this diagram. Find the magnitude of the resultant of the 6 newton and 10 newton forces and the angle between the resultant and the 10 newton force. So we're going to find the angle between the resultant and the 10 newton force. Now the sensible way to do this is to actually add our two forces together to find the resultant. You can add two forces by putting one on the end of the other. So let's put the 6 newton force on the end of this. They are vector quantities, remember, forces, and you can add vectors by putting one on the end of the other. So the resultant is just going to be this vector here. That's our resultant. Now if this is 110, this must be 110, so this must be 70. And we know this one is length 10, this is length 6, and we can find this using the cosine rule. So r squared will equal 6 squared plus 10 squared minus 2 times 6 times 10 cos of 70. r squared is equal to therefore 94.957 when you've put that into your calculator. So r comes out to the square root of that, which is 9.74 newtons. Now, we want to find the angle between the resultant and the 10 Newton force. So here's theta. The angle between the resultant, r, and the 10 Newton force. So we can solve this by using sine theta over 6, the opposite, equals sine 70 over r. So therefore, we know r is 9.74, so theta over here will equal, if we do 6 times sine of 70 over 9.74, remember to use all the values, times by, got an inverse sine of all of that, work that out, and then inverse sine of that. Done a few steps there, I hope you can keep up. When you've done that, you should get 35.35 degrees. So that's that angle here. Now, the two forces act in the same vertical plane. The particle P has weight 20 newtons and rests in equilibrium on the surface. Given the surface smooth, find the magnitude of the force exerted on P by the surface. So what we've got here is we've got that force 6 and we've got that force 10, and then we know that it has weight P, weight 20 newtons. Okay, and there's going to be a normal reaction on this. Okay, we know it's in equilibrium. Now, if we know it's in equilibrium, then there's only these two, the normal reaction and this are both vertical. These are the only two horizontal forces, so they must balance each other out. So if they balance each other out, that means our resultant must be going vertical. Okay, this angle combined with this angle must be 90, because otherwise it would not be in equilibrium. If that resultant, now I've got to be careful here, that r is very different to this r here. This is the normal reaction of the plane on the particle, and that was my resultant of these two forces. So this is a reaction. Sorry, I'll just get a blue pen. Reaction. And this one here was the resultant. Okay, so don't confuse the two, they're totally different. This one is the combination of the 6 and the 10. This blue one is actually the combination of all these, well, not the combination of these three, is going to be the 20 minus the resultant, the 10 and the 6. So our reaction will equal the 20 newtons here, minus the resultant that we had before here, because this must be acting vertically. That's our resultant. That's what that 10 and that 6, they're pulling it up, and the 20 is pulling it down. So 20 minus 9.74, which gives us 10.323 SF, when we calculate that, is what's going to be pushing up from the floor, or the surface that it's on. Last part of the question. Find the angle between the surface and the 10 Newton force. Well, we know that our reaction and our resultant must be vertical. We know that the angle between our resultant and the 10 was 35.35 degrees. And we know that that's going to be at right angles, because remember the resultant was vertical because of the 6 and the 10. So this angle must be 90 minus 35.35. So we get 54.623 SF. Now this question caused a lot of problems, mainly because the students mainly tried doing normal resolving to get the components. Now I think they tried perpendicular, vertical and horizontal, and got into quite a lot of mess on that because they didn't quite work out what this angle was and what this angle was, because it's not easy to do initially. Another way you could have done it, if you didn't want to do it using sine and cosine rule, you could have actually decided if we make this direction here like our x direction and this direction our y direction, Okay, we could have resolved in those two directions and added up all our components, and then you could have found the resultant of those. And what that would give you, it'd give you an x component for the 10 and a y component for the 10. Okay, in fact, all of it's going to be 10, isn't it? It's going to be 10, 0. And then you're going to plus on that a minus x component here for the 6, and you're going to have a y component. And you add these up, and you get some values here and here. That squared plus that squared will equal the resultant length of the resultant force. So you could have done it that way. And then you could have found the angle to the plane because you got that direction and that direction from this plane. So you go that much along and that much up, and then you could find the angle using these two components. And that is another way to do it if you want to resolve in two perpendicular directions, making sure one of them is the 10 Newton direction, and then life becomes a lot easier. If you make it in the direction of the horizontal, it becomes very, very tricky indeed. Right, so there you go, 2 questions. What I suggest you do, if you just pause the video at the beginning and you found those a little bit tricky, then I would suggest you save those questions up to have another go at again, because they are definitely the sort of questions you need to understand if you're going to get the top grades in your maths A-level on the mechanics side.